Your assignment is available on the Canvas. So submit online. You do handwritten, take your phone, take photo, convert into PDF, and then submit into the Canvas. Okay, chapter 7, we start to link the equation that we learned in chapter 6, link with work and energy. Okay, we're going to convert all the force, all the distance traveled into work and energy. So what are the force we have? We have kinetic energy and so on. Okay, we start with kinetic energy. So rigid body will go through 3 motion. Translation means move in this way. Rotation, and then combination of 2 become general plane motion. So as you can see here, you've seen this one before. You have rigid body and you have a reference point from point P, X, Y, and then there's one point on the body of the rigid body. So when this body rotates anti-clockwise, angular velocity, so this one, your thumb point out, so your W is in positive K. Then you have a velocity at this point, your interest point, VI, and there's a V at the point P here. Okay. The rest you read. What is important, you still use kinetic energy equation. Kinetic equal to half mv square. Still the same. But you only need to be careful because when you calculate velocity, this component, you need to be careful that this is a vector. So vector here again, you are referring from somewhere. For example, this equation, V equal to VI equal VP plus VI slash P. So you have this vector, and this vector. Okay, so still, if you refer from VI slash P, V of this one from P, you write like this one. So just a cheat code, you just convert this one into negative. Then you arrange the equation, you will get VI equal to VI plus VI slash P. Okay. So the rest you work with vector, right? The rest you work with vector. So I'm going to skip all the derivation steps. This one you read as your reading time. There's a lot of mathematics, right? You won't be asked the derivation steps, right? You'll be asked on the application of equation. So at the end, very long, you see a lot of equations. I just need to highlight what are the components you get after you do all the integration. You have the effect of the mass effect. You have the center of gravity effect. And the last one is the moment inertia effect. This is the difference between particles and rigid body. So when you have rigid body, you have a center of mass G, you have moment of inertia, you have the mass effect. So you need to consider these 3 when you work with rigid body. Okay, mass, center of mass, and moment of inertia. So the first one, you are looking at half mv square. This one is the one you learned in chapter 1 until chapter 5, the particles one. But when it comes to rigid body, you need to calculate the center of gravity. You need to know how to calculate back what is your x average and y average. And then your center of, this one in chapter 6, We learn about lots about this one, right? Okay. At the end is just need to add one more to the kinetic energy equation. The one that I highlight with box, this one you learn in particles, the effect of mass. The second one is the effect at your second moment of inertia, right? So for rigid body, you add one more component at the back. It is half omega square I at the center of gravity. So this one you refer to chart. There's a chart there. Okay. Okay. So again, this you'll use a lot of time if you need to calculate kinetic energy. Okay. So let's say you have a translation. Translation means move in a straight line. So translation, you don't have rotation. You don't have angular motion. You don't have angular acceleration. So the second part here, 0. Okay. Yeah. Again, this is the general equation when you come to chapter 7, when you need to calculate kinetic energy, half mv square at the point of center of mass plus omega square, half omega square Ig. What about when you have rotation? When you have rotation, you have both. Need to consider the omega component. Then you need to link back. Usually the question won't be directly, sometimes won't be directly give you all the information. You need to recall the definition of omega and r. You can convert it into velocity. So v equal to omega r. Okay. Okay. So you can rewrite the equation. Sometimes you don't have the velocity at the center of gravity or center of mass. You need to convert this one from the question. Will give you the radius from the gravity r and then omega. Usually you will see omega. So you take omega r, you get the v. Substitute back here, you get the total kinetic energy for the object that is rotating. When you combine, right? When you combine, again, don't go and memorize the equation. It's highly recommend you memorize the general one. So this half mv square plus half omega square Ig. You memorize this one. Then you memorize v equal to omega r. You don't go and memorize the n one because it might be different when it come to different combination of object. Right? Okay. So this is only one object. So if you have one object, when you combine, again, another kinetic equation, T equal to half IO omega square. What is IO again? It's not same. IG means IG. IO means you need to take IG plus half, plus MD square. So there are two set of equation. Both give you same answer, but once you're referring to the different point, on the left-hand side equation that use IG, this one you're referring to point G. The one that I write on the right-hand side of the whiteboard here, you're referring to the point O, or the reference point, or any point on the object. Then you need to convert IO with IG plus MD square. What is D again? D is a distance from the reference point. This one, IG, again, refer to the chart. Don't mix with IO and IG, so different case, although both give you correct answer. So, and then don't confuse between the two equation. Right? So general plane means combination of two. So combination of two, still you need to use back the two lah. Half mv square and half omega square I. So sometime we will use the IC point. Okay, the IC point. So if you use the IC point to do calculation, you can simplify the above with a half IC omega square. Okay, this is a kinetic. What about work? What is work? Work when the force travel with a certain distance, right? What is work? Work is force S. And both must be parallel direction. Both are vector. So same with this rigid body. Okay, same with rigid body. So if you refer to this diagram, your energy, not energy, your work equal to integration of force and dr, means the distance traveled by the force. So you just convert the equation. Okay, of course, this one we won't ask you to derive. So if you have a constant force, just to remember, you are focusing on the direction of where you travel and where's the force pointing to. Put the force and your surface direction same. You only focus on that, right? Although your force have lots of direction, always split your forces parallel to your surface. Then you'll get the work, the work done by the force. So that is only need to be highlighted. Like for example, this case, you just split your FC here into X and Y direction. Again, perpendicular to a distance, don't create work. Only parallel, same direction. Okay. Weight also done work because weight always pointing down. So if that object fall from high point to low point, it will create work. So just be careful if you're given a datum. So then there is a positive S and negative S if you refer to datum. Same with the one that you learn in particles. Right? So this one you see is moved from a low ground to high ground. The datum is here. If you move to high ground, you have positive Y, you get positive work due to gravity. Okay. This one is your, it depends, it depends on that one. Okay, this one is, there's a negative because the direction of W. Okay, the work done by weight is negative is because your weight is pointing down. Although your displacement of your height is positive, go up, but the weight is going down. Okay, this object was moving up. So if your object move down, then your work will be positive because your weight is pointing down. Your Y is negative because this is datum, right? Below datum, negative. The negative, we get positive work. So this is also same. Need to highlight. Also part of the mistakes. That always there will be mistakes in this one. When you deal with weight, be careful on the displacement distance and look for the reference point. That one is your means original position is your datum. If you move up, you get a negative work. If move down, you get positive work. Okay, this one also important. This one, you will be seeing spring in your final. You're seeing spring in your final. So the force of the spring, always you take coefficient of spring multiplied by the distance traveled by the spring, right? Okay. So this one you're familiar, right? So the work done by the spring is half kx squared. And there are some forces that do not do work. For example, the normal force do not do work because normal force always pointing at perpendicular to the distance. Do not do work. If you have body that always rotating at a flat surface, for example, this one, the weight is pointing down, but it doesn't move anywhere, right? The weight always pointing down. Okay, so this diagram is important for your coming assessment. So again, your weight and normal force do not do work. Just I need to highlight this one. Okay. Okay. Okay, this one also I need to highlight. Friction force acting around round bodies as its roll without slipping over a rough surface also does not do work. Okay. We have done with the work, then we continue with moment. Again, what is moment? Moment is force multiplied by the perpendicular distance. You can convert your moment. You can transfer your moment into couple forces. Okay, you can convert moment into couple forces. Coupled means positive and negative direction of each other, and there's a distance from center. Right? So the rest is derivation of equation. So you know that here multiply by force, you get the moment. Right? You have one moment here, one moment here. Total, you get one full moment. Your radius is half. R divided by 2. This one you convert from this big moment. This big moment rotate like this, so your force will 1 point up, 1 point down, so that this object rotate this way. It rotate at the center. You combine the moment on the left, moment on the right, because these two forces, you get total moment. Okay. So this is a small dissect of triangular. So still same, you use the equation of a small section of circle, theta, s, and r, s equal to r theta, that equation, to derive the equation. Right? So I will not go deep. So if you have a coupled moment, like this one, you use a new equation. I think this one is a new equation for today that you learn. The work done by the moment, work done by moment will be the distance traveled by the moment. So in this case, distance traveled by the moment is angle. So you take moment, multiply by the angle traveled by the moment, or changes. So here you see m bracket theta 2 minus theta 1. So basically is the change of angle. Okay, so this is something new for all of you for today. So moment will create work in rigid body. You don't see this one in particle because particle is one dot. So you, one dot, it's very hard to calculate whether this dot rotate how many degrees. It's very hard. But rigid body you can. So moment, you can create work. So how to calculate work done by the moment? M multiplied by the change of angle. This is something new when you come to rigid body. So we go for example of the chapter 7. So you have a spring body, you have a slot here, you have a rod here, and this rod rotate clockwise. Rotate clockwise, what happened to your direction of your omega or alpha? Negative. If you turn into vector, because clockwise is going in, your thumb going in, so your alpha and omega will be negative k. All right. So there's a distance between the B position 0.75 and there's an additional moment given in the diagram, M, for rigid body, and you have been, you learned something new just now. Moment can create work. Moment can create work. Moment times the distance by the angle changes, it will give you work done by the moment, right? And there's a P force here. So you know that when the P force press down, the spring will stretch. When the spring stretch, there is a energy generated or the work done by the spring. Okay. And what else? Point P always applied perpendicular end to end of the bar. Perpendicular end of the bar. So this one, the end of the bar, it will rotate in the circular motion. If you look at here, point P perpendicular. So when you continue to press perpendicular, this rod, this end here will move in the circular motion. So the spring has an unstretched length. Original length was given 0.5 meter. Remain in a vertical position due to roller guide in B. We always maintain as a vertical position. Calculate the total work done by all the force acting on the bar when it's rotate downwards 0 degree to 90 degree. You need to calculate the total work done by all the force acting on the bar. You focus on the bar and then you look at what are the forces acting on the bar. So how many forces act on the bar before you start? There's a point pin here. When there's a pin, there's two forces. Right? When there's a pin, there's two forces. A point here, there's a pin, there's a moment, there's a spring force. So spring force is pointing out or pointing down. The spring force, why point down? You are the rod, right? So let's say this is a spring. What do you feel if you are this body? So don't confuse with, always focus on this one, spring. Okay. The numbers, I won't be very focused on this example. I just want you to observe how we solve the question. How you draw the free body diagram and kinetic diagram. So the rod have a pin. All the pin will have X and Y direction. In this case, your X direction is to the left. Right? And this one was pointing out. You have AY and X. Then spring point up and P perpendicular to the end of the spring there. What is missing in this free body diagram? And beside moment, what else missing? Weight. Okay, don't too excited to solve. Always start with the center of gravity and then point your weight down. Yeah, and moment. Okay. Then the theta, your spring, the rod is swing from 0 degree to 90 degree. Yeah, then you put in all the parameter. The length, all these help you to find moment and distance traveled by the force. Okay. Okay, we start, we calculate all the force. We look at W, how far the W traveled from 0 degree to 90 degree. How far from here? From 0 degree to 90 degree. W, you know how to calculate lah, mg. The displacement is 1.5. Why 1.5? What is the length of the rod? Length of rod is 3. Where is the center of gravity? At the center, right? So center, all the rod at the center, it always travel half, right? 1.5. Right? Okay. So again, is you are looking at the weight direction. It travel from 0 to 1.5. Yeah, so that is one. And then y positive. Y positive. Your W is negative. Your position H or your S is negative. Because your reference point is here. Your datum is here. You move down. So 2 negative, negative, you get positive. If you move up, then you get negative already. Okay. So you have done weight. Everything that you draw on the free body diagram will give you work. Unless is it do not move lah. For example, these 2 points do not move. Then no work. Okay. So what about moment? Moment do work. How moment do work? By change of angle. You take moment, change of angle. But your degree you need to change to radian. You cannot use degree anymore. You have to use radian. Okay, you are moving 90 degree. 90 degree is pi divided by 2. Okay. Yeah. 360 is 2 pi. 180 is pi. 90 degree is half of the pi. Okay. So your work done by coupled moment will be m times the change of angle, 90 degree. So 50 multiplied by pi divided by 2, you get positive work. Okay. Spring. Spring half kx squared. So when theta 0, spring stretch 0.25. Why 0.25? Because original is 0.75, the original length of the spring. Let me look back. I forget the original length already. The string has stretched. Okay. and remain vertical position. Okay. Unstretched is 0.5. That's 0.5. Okay. Okay, so unstretched already have 0.75. Let's see, length here is 0.5, and then the distance between B and A is 0.75. So here, from the reference point here, to the body of spring until here, I have how many? Okay, the length of spring is 0.5. Then here to here is 0.75. So when you install before you move, so the spring will be 0.5 here, right? So there's a remaining 0.25 there. Yeah, so it's very hard to, this is not scalable diagram. So this spring actually shorter than this distance. So when you do the displacement distance, just be careful lah. So at 0 degree, the spring was stretched 0.25. Before you start, you already stretched already. Okay, because the length of this spring was 0.5. The distance between the location of B until the rod here is 7.5. So this rod, when it's horizontal, you already stretched 0.25 already. So there's an energy installed inside the spring already. It charge up. Then when it's 90 degree, so means this spring was like that. Right, this one was vertical. So it's like stretch until maximum already. So when you stretch, you stretch 0.25 lah. 25. Okay. So there's a distance, you use the calculation minus half kx squared minus half kx squared. You get negative value for the spring. Okay. Once you calculate the spring, what happened to the force? Force, again, be careful. How force create work? It must be parallel to the distance it travel. So here, the bar move downwards, the force displaced through a distance of half pi 3 meter. Why 3 meter? You know how the equation you calculate? You have you know this equation, right? Theta, S and R. So how to calculate displacement? R theta, right? So now your force travel from this location, P, until this location. This is the distance traveled by the P. Your angle here is 90 degree. 90 degree is pi divided by 2. So your S equal to R theta. Your R is long the distance here. The rod is 3 meter. So 3 times pi divided by 2 is a distance traveled by P. Because P, it tells you it always perpendicular to the end of the distance. Okay. So you get positive work done by the P. In reaction, no work because doesn't move. So total work, you add all the force, all the work done by the moment, weight, spring, and P. Okay. All right. And again, your incoming assessment will deal with spring. So this example 1 is important. Principle of work and energy is no longer something new to you because you learned this one. And okay, so what is principle of work energy? Means you equal the work done equal to energy. So what is happening here? You only focus on kinetic energy. So kinetic energy before plus the work done equal to kinetic after. Right. So don't confuse principle of work and energy with conservation of energy. Yeah? Don't confuse these two. Conservation of energy means you only deal with energy. And when you have energy, there is a potential energy you need to consider. So principle of work and energy, you don't deal with potential energy because the case will always move in the straight line. And there is no changes of position of reference point. Okay, so here, because you are dealing with rigid body, again, you need to consider the translation, rotation, kinetic energy, and the work done by the external force and moment. So rigid body, you need to consider moment and all the force done. Okay, so I'll give you one example. So example number 2, you look at this diagram here. So you have a pin rotate clockwise. So clockwise, if you use the right hand rules, it will be going in. Okay, your negative k if you do vector approach. So the moment given, radius given, the spring was given. Spring coefficient was given. There's a pin here. So mass was given. It was supported at the center O here. Determine the angle through which it must be rotate. Means how many angle you need to rotate this to attain an angular velocity of 2 radian per second. Means you need to rotate what, and because of the spring effect, you will get omega equal to 2 radian from rest. It acts upon a constant couple moment given 5. So given a moment there. A spring is original unstressed and the coil warps around the rim of the disc. So of course, this one won't be the standard of assessment. The assessment will tell you what kind of equation you need to use. For example, the first one, normally you'll see it will force you to draw free body diagram and kinetic diagram. The marks will be from 7 point to 10 point, 10 marks. So out of 25, you're almost half of the marks already. Okay, then the second half is all the calculation. So the calculation will mention very specific, like applying the principle of work and energy, find something, find what. Okay, so here you cannot run away from the free body diagram. So you draw your free body diagram. First one, always draw your weight and pass through the center of mass. In this case is O. Then there's a pin there. Pin always have two forces. Then there's a moment given. And then there's a spring force acting at the end of the disc. What is the direction of the spring? Point in or point out? What do you feel if a spring tied to your body and you need to rotate this way? What do you feel? You pull out, right? So the arrow was pointing down. Okay. So don't confuse with the spring, because the way you draw, it will give you positive, negative answer already. Okay, so by applying the principle of work and energy, so you use kinetic energy, T1 before equal to work equal to T2. So kinetic energy, you have lots of things to operate here. So because it's rotate from rest. So kinetic before 0. For your assessment, don't leave this blank. You need to write this statement out to get 1 mark for the answer. You need to write T1 equals 0. Okay. T2, after the rotation, your T2, you use half IO omega square. Again, there are two ways of calculating kinetic. One is the half mv square plus half the omega square Ig, or half IO omega square. So in this case, we use IO to do calculation. So IO equal to mr square, because it's at the center of this, so we can straight away use this equation. Half mr square or md square, same. Okay, so this one, you look at the chart. You go through the G. So G is z-axis is this one. Okay, this equation, you modify the R according to the diagram. So you substitute value, you get this one. Okay, next, the work done. The pin do not do work. So these two O forces you take out. This one also you need to write this statement if you're being asked to use this equation. Those that do not do work, you need to mention in your answer. Yeah. So if you don't write, it means no marks. You write, then at least you got chance to score some point there. So in this case, the pin forces do not do work. To score some marks, please write whatever that do not do work, write them in your answer. Okay. Okay, then M rotate certain angle, it do work, so M multiplied by change of angle. So here you need to find the angle. You need to find the angle. So this you have one unknown there. Okay. Spring do negative work. Spring half kx square. So you have before and after the spring. The spring was unstretched. So you need to find the distance traveled by the spring. Right. So also there's one missing parameter here, which is your S. All right. You don't know how much is stretched but you are given the final direction. You need to find the velocity to find. So now again, the ultimate purpose of principle of work and energy, when you use kinetic, the final target of using this one, always finding velocity. Okay, this one, the final intention of using this one, always finding the V, either before or after. Okay. So you have the moment work and the spring work. So you substitute inside. Kinetic before don't have a kinetic. After you already calculate. You substitute the known one. K was given. Again, how to calculate the distance traveled by the spring? By S equal to R theta. S equal to R theta. And then square it. Here you get a quadratic equation. You get quadratic equation to solve theta in the square. You solve for quadratic, you get in radian. Remember the answer in your formula here is radian. Remember to change it into angle. Okay. So when you have angle, so this is the answer that asked by this question? Huh? Which one? This is the work done by the moment. US is the spring. The spring done by the work. Okay. Okay, I think we go one more, then we call it a day. Yes. Yeah, can. Okay. Okay, again, you keep seeing spring already. So spring is very important for your assessment. Okay, so same procedure, but now they change orientation only. You have same moment given, point G was given, and the spring tied to the one and the point of the disc, but now different orientation. So mass was given, gyration, radius was given, center of G given. Again, when you see gyration, you need to use this one. Sorry, this one. Ig equal to mk square. You see gyration, the background intention is to see whether you know how to use this equation or not. Okay, you see gyration kg, you need to find Ig already. Ig equal to mk square, mkg square. Okay, subject to clockwise couple, row from rest without slipping. Determine its angular velocity after the center of mass move 0.8 meter, 0.18. Mean this one scratch 0.18. So 0.18, you can calculate the angle rotated by this, right? By using this equation, S equal to R theta. This one was rotate distance of 0.18, right? 0.18 is your S. You have your R is 0.25. You can find your angle. But here, angle here is in radian. When you want to use for moment, for energy or moment here, this one is in radian. Yeah, is it in radian? Let me check. Yeah, in radian. So this one is in radian. So back to this question, spring was given and unstretched. So still start your question, first part of the assessment question, part A you'll be forced to draw free body diagram and kinetic diagram. So if you do not see a kinetic diagram, you still need to draw kinetic diagram also, because you need the kinetic diagram to solve the calculation, because you're using F equal to ma. You need to show your A direction, right? So kinetic diagram, free body diagram, if you look at example 3, start with your weight from the center of mass. Then rotation, M, and the spring. Again, spring is go in or go out? Go out, because it's pulling from here. Okay. Then there's a contact surface. So just now, don't have contact surface. Here don't have contact surface. But here got contact surface. So contact surface, you have normal force and friction force. When you have a contact surface, sure put inside these two. Why this direction? Because you're rotating this way. And the friction force always against your motion. So pointing this way. Again, before I forget, for your final, look carefully. The question will mention a vehicle with how many wheels. So you need to find the friction of each wheel. Look carefully. Look carefully. You're having 3-wheel vehicle. You need to find the front wheel, back wheel. Back have 2 wheels. So be careful. when you do calculation, how many wheel at the back? 2. So when you do calculation, you have 2n and 2 that one. But if you can simplify your diagram with only 1, but you have 2n. You don't need to put 2f, you just put f, because this one, how you find friction? Mu n, right? This one you substitute here. Or you can write 2n. Okay, so actually I leaked some of the question already, so just be careful. Okay, then kinetic diagram is the angular velocity or acceleration. So this one move in clockwise. Velocity move to the right. So V at the center of gravity. And there's in this case, I use IC point and point A. Okay. So pull out the equation of work and energy. So you do the work before. So here it is mentioned from rest or not? From rest. So no kinetic. Again, don't miss out this in your answer. If it do not move, stretch, you want to score 1 point, write this one. P1 equals 0. Don't assume me, I know. Okay. Then T2, because it's rotate, so you use half IO omega square at the point number 2. Okay, T2 equal to half IO omega square 2. Again, if you use IO, what is the format? IO equal to IG plus MD square. It's a different from if you use IG. In this case, we use IO. So IO, you have 2, MK square plus MR square. Okay. So this is using gyration, MR square. So you substitute value, you get 1 in omega term. So this is something I need to highlight. So yeah, this one is focus on IO. Okay, work. So what are the things that do work? Normal do not do work. Weight do not do work. So spring and moment do work. Friction, what friction do not do work? It tell you what? Without slipping. Okay, I go back to one of the slide. Early. Okay, where is it? Here. Okay. Yeah, this statement important. Friction force acting on a round body at its row without slipping over a rough surface does not do work. If you see the question, row without slipping, you need to write friction force doesn't do work. This statement you write, you get 1 point. Okay. Okay, continue. So spring, half kx square, before minus after. So after minus before, you get negative. Moment do work, moment multiplied by change of angle. Right? So wheel does not slip, so when you move 0.8, again, you use the S equal to R theta, you find how many angle it moves. The angle is 0.72 for your reference, for your homework, for your revision check. So you substitute inside there. Right, you find your S. What is the distance traveled by the radius of this? You substitute all the value there. Kinetic 0. Work, you have 2, moment and spring, and the kinetic after. What else? So there is a you need to tell the omega direction. If you can draw the direction in your kinetic diagram. If you don't want to write direction in your final answer. Okay. Again, this one is trivial question. Okay, so I think we stop here. Then we continue next week. Example 4. Okay. Okay, we stop here.